And there we are. Take it away.
Can I share my screen, Jana, or is that not?
Yes. Let me give you the screen.
I'm in the screen sharing queue, so it should be working.
I see. Yep.
Okay. Can you see it and can you hear me well? Can you hear me?
Yes.
Okay. And can you also see my screen?
Yes.
Okay, thank you. So, hello everyone, I'm Sylvester Nádas, and with my co-authors, we are interested in internet resource sharing. So, we run some testbed studies on fairness, and we chose BBRV2 congestion control as a new level of congestion control to compare to existing ones because it's designed to be friendly to cubic flows as opposed to V1. It has scalable ECN response, and it already has some deployments. So we use 3 machines connected in a chain topology in our testbed, a traffic generator, receiver, and the bottleneck in the middle. And on the sender and receiver, we installed the BBRV2 alpha kernel, and we used default Linux settings. We implemented several AQMs in DPDK, tail drop, pi, GSP, step, pi square, dual pi square, and virtual dual Q core stateless AQM. We use NetM delay for RTT emulation of acknowledgements to emulate RTT. The bottleneck rate was changed between 100 meg and 10 gigs, and the results I present are with 1 gigabit per second. And we use several congestion controls, cubic, BBRV2 in both scalable and classic mode, and DCTCP. We changed the number of flows from 2 to 100 in these measurements. So this is an example measurement results. We have 2 connection classes. Connection classes are identified by congestion control and RTT. So this was cubic 10 millisecond and BBR 10 millisecond RTTs over a 1 gigabit per second bottleneck. We changed the number of connections. Half is from one connection class, the other half is from the other. The buffer size is set as a factor of the RTT, so 0.5 means 5 millisecond in this case buffer. And we plot the relative good put, where 1 is the ideal and the relative good put of a connection class is the average good put within the connection class divided by the ideal per connection fair share. And we also studied several AQMs. So we have seen reasonable fairness with tail drop when it comes to sharing between cubic and BBRV2. It was much worse for small buffers. And we also have seen good fairness with CCSAQM for basically all cases. So what happens with the different AQMs? We plotted the tail drop results, a gray shadow for reference. So with pi, the fairness was very similar to tail drop. While with GSP, we have seen huge degradation compared to tail drop for a smaller number of users, and it was similar to tail drop for a larger number of users. So what is CCSAQM? Mentioned as a result. So in addition to existing AQMs, we also evaluate CCSAQM, which is a core stateless resource sharing framework. It can apply a wide variety of policies, not only fair sharing, and it can enforce these policies for heterogeneous traffic mixes. And it also scales well with a very large number of flows because the algorithm itself is stateless. And it's also congestion control independent. It puts no assumption on how the congestion control behaves. It relies on packet marks with different values. Larger values mean more important packets. In congestion situations, packets with smaller values can be dropped or marked with a congestion experience DCM flag. And the bottleneck behavior is purely based on the packet values. So we don't have to do any flow identification. We don't have to use separate queues or decode the policy information in any way. Therefore, the implementation can be very simple and fast. At the same time, it needs some standardization, or it has to be done within an administrative domain because it needs a header field. Even though the AQM is almost like the existing tools that we were able to implement it in P4, you can find much more about it at our homepage. So getting back to results, We also used DCTCP-like congestion control. So we compare the fairness of DCTCP and BBRV2 in scalable mode. In this case, instead of changing the buffer size, we changed the target delay as a factor of RTT. And our key findings here is that while the step AQM prefers DCTCP, pi square AQM, for pi square, the BBRP V2 is the winner. And it's actually hard to choose which one is better. For pi square, the fairness is improving as the number of flows grows. By which step it gets worse for larger number of flows. And the CCSAQM, as mentioned before, it provides a reasonable fairness in all these cases. Again, this was the relative throughput I have also shown for the BBRV2 versus cubic cases. So let's see how these AQMs are marking the connection classes. The ECN marking ratio here shows what is the fraction of the congestion experienced marked packets compared to the total number of packets. It's a logarithmic scale on the y-axis. It is clear that step and pi square, both connection classes are marked the same. And because the two congestion controls use the ECN feedback differently, this results in bad fairness as shown in the previous figure. And with CCSAQM, there are seemingly no connection with the marking ratios of the connection classes, so there is no clear formula how to mark the packets. But this is exactly the right marking ratio to achieve good fairness. We also compare the fairness between BBRV2 scalable and cubic flows over dual pi square bottleneck. In this time, I present time series plot, and the number of flows from the different classes changes between 0 and 50. You can see the number of flows at the top. And you can see that dual pi square can control BBRV2 alpha traffic class, leading to significant unfairness between the two traffic classes. In general, when the number of BBR2 flows is large, the classic flows experience very small throughput. So please be aware that this is a logarithmic scale. You can see the total class throughput at the top. And we believe that this is because BBRV2 applies a model-based congestion control. But what happens if the network works with different model? So this kind of unfairness can happen then. And comparing that to dual Q core stateless AQM, that can provide a pretty good fairness by not assuming anything about the congestion control used. So in summary, we have performed much more testbed measurements. I will have a link to all the results. But most congestion controls have RTT fairness issues even in mono-congestion control scenarios. And evolved congestion controls have fairness issues with legacy. BBRV2 versus cubic fairness is very dependent on settings. I actually shown some good results. Sometimes it can become quite bad. And DCTCP versus BBRV2 scalable mode in general provides bad fairness. And then an interesting finding we have seen is that AQM tunes for a specific congestion control have actually the potential to hurt the coexistence even more, and they very rarely help it, even though they help in, for example, multi-RTT scenarios when the specific congestion control is used. So there are examples for the graded performance compared to teardrop or span, and it's pi and GSP for BBRV2 versus cubic, pi square for DCTCP versus BBRV2, and dual pi square for BBRV2 scalable mode versus cubic. So in summary, the congestion control evolution has accelerated. It's also possible to do user space congestion control or congestion control in BPF. But it's very hard for a new congestion control to be both innovative and to be fair to existing congestion control. So we don't want to say in any way that BBRV2 is a bad congestion control. We believe it's actually a quite good one. But as also stated in reference number 1, TCP friendliness greatly constrains how we can handle congestion in the internet. And why fairness to existing congestion controls is often demonstrated in special cases, that is not universal. And as the number of deployed congestion controls increases, this becomes even harder. And even the harm-based bar for a new congestion control is close to impossible to meet. So this is, I refer to the presentation which Jana mentioned at the beginning. And I believe that two congestion controls can be still tuned to be compatible for some scenarios, but we are skeptical that this can be generic enough, or this can be done among several new congestion controls. So what can be done? How can we provide fairness? What are the way forward? So today, fairness is dominated by end-to-end congestion control and over-provisioning, and we question whether this is still the way, or whether actually TCP friendliness to Reno and or data center TCP a point of ossification, and the similar point of ossification is AQMs tuned for a specific congestion control behavior. There is other method used quite often, that is fairness scheduling by scheduling in the network, for example, FQAQMs and hierarchical QoS. And this is working quite well. It has its issues. It's not practical for high-speed users. It results on equal or static sharing, which is not always optimal. And communicating policies to every potential bottleneck is hard. So we believe that cooperative approaches like CCSAQM has a good potential for controlling resource sharing. Flow identification and policy decisions are done at the endpoint or at the network edge. In this case, the implementation in the routers is then very simple and invariant to the number of flows or invariant to the policies used, though it requires a header field. But to be on the fair side, headers or some kind of solutions are needed for many other solutions, like we have ECN, we have an L4S bit, or we are proposing an L4S bit, and also there is the SCP. But this one requires a new header field. So to compare these solutions, created a table with the three methods: end-to-end congestion control, in-network, and cooperative sharing. So end-to-end congestion control provides fairness by congestion control, but it has fairness issues, and the RTT unfairness is hard to solve. In-network scheduling provides very good fairness and actually solves RTT unfairness, while cooperative resource sharing provides fairness by packet marking plus AQM. It provides good fairness, and it also solves the RTT and unfairness issues. So resource sharing is dynamic for end-to-end congestion control and cooperative, and pretty static for the in-network solutions. And the end-host control, the end-to-end congestion controls has a full illusion of the end-host control. And I'm saying illusion here because there is still a fate sharing of packets, and also congestion control aggressiveness and RTT is very chaotic and actually hard to control. There is limited control of end-hosts in the in-network scheduling scenarios, and with the cooperative, if actually the marking is done at the endpoint, there can be high amount of control, while it can be limited if there is edge marking. So it's if the end-host is not communicating with the edge. And congestion control evolution is constrained by end-to-end congestion control based fairness because of the harm to existing congestion control, and it's less constrained in the two other cases. And the bottleneck complexity is low for end-to-end congestion control. This is basically the bottlenecks we have today. We don't have to change anything. For the in-network, we believe that in most cases, some kind of CPU-based solution is needed, especially for high number of flows, or especially if you want to control hierarchies of resource sharing. While it's medium for cooperative, we were able to successfully implement the AQM in P4. There is no need for signaling for end-to-end congestion control. There is a high need of signaling for every potential bottleneck in the in-network case. And depending on how we do marking, some kind of signaling might be needed. And actually, the packet marking is a kind of in-band signaling also. Also, the end-to-end congestion control is the current state of affairs, so it doesn't require standardization. The in-network likely requires some signaling unless we are okay with the per flow fairness, basically. And the cooperatives requires some kind of standardization for packet marking. So questions to community future work. first question is what more to include in these type of evaluation, congestion controls, AQMs, RTTs. Also, what are the typical implementations when it comes to operating systems and meaningful defaults of the congestion controls? Also, a very important question to discuss is that what are the typical bottlenecks? What is the speed of them? How many flows do we have over them? And how many bottlenecks shall we consider in the path? And the third interesting question is the effect of the sub-millisecond internet on fairness. So some caches are very close to the edge. And do non-CDN flows still have a chance when sharing a bottleneck with these sub-millisecond flows? So you can find our results at these web pages. And I'm looking forward to your questions and comments. Thank you.
Sylvester. Koen is in line. Go for it, Koen.
Hi, Koen here. Can you hear me?
Yes.
Yes.
Okay. Thank you for this work. It's very interesting, and I think it opens also a very interesting discussion. Because indeed, from L4S point of view, the strategy here is to try to line up long-term congestion controls to be fair, so that the AQM, like you showed, doesn't need to make differentiation between the different types of congestion controls. Well, for L4S, we did a big hub between the classic and L4S traffic. So I think it's very valuable to do these comparisons, definitely. It's also a good discussion whether we should do this differentiation or not. From within the network, and whether the network is really responsible for doing this, or that we also should focus also on the cases where it's not possible to do something in the network, to also make sure that congestion controls really have a common protocol and a common behavior related to ECN marking, definitely drops, but also I think it's more important to have this behavior on a longer term. Yeah, I think it's a good point for discussion. And as you know, L4S is relying on the end systems to do at least their best they can do to line up.
Mm-hmm.
I don't know. Yeah, I guess it's up to other people also to have this discussion. But thank you for the work. It's very useful.
Thank you for your comment, Koen.
Thank you, Koen. And thank you so much, Sylvester.
Thank you.
I would again encourage the conversation to continue on the mailing list. This is for the presenters as well as for the other folks in the group. Please go ahead and kickstart conversations on the mailing list. I think that's a much higher. You can have much deeper and higher bandwidth engagement there. All right.